Hi viewers, welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In this class, we will discuss the topic, the Greens Theorem. This is BSc Physics first year, Mechanics and Oscillations, Semester 1, Unit 1 syllabus. So in this, the contents we are going to discuss are the Greens Theorem in a plane and a statement. After that, we will discuss the Greens Theorem in a plane and its proof, and we will solve the problems based on the Greens theorem. Lastly, we will see the conclusions, and also we will cover the discussion of Greens theorem identities.
Yes. First, let us see the statement of Green's theorem. Okay. So that is, if S is a closed surface in XY plane, S is a closed surface in XY plane bounded by the closed curve bounded by the closed curve C, and capital M and N are continuous functions of X and Y. Continuous functions of X and Y respectively, and having continuous derivatives in S, continuous derivatives in S, then the mathematical expression for Green's theorem is closed integral over C m dx plus n dy is equals to surface integral over S dou n by dou x minus dou m by dou y dx dy. Dx dy. This is the expression of Green's theorem. So let me repeat. If S is a closed surface in the xy plane bounded by the closed curve C, and M is the function of x and y, and is the function of x and y, and their derivatives dou m by dou x, dou m by dou y, dou n by dou x, dou n by dou y. So they are having the continuous derivatives in that closed surface. Then the Green's theorem statement is closed integral over C m dx plus n dy equal surface integral dou n by dou x minus dou m by dou y dx dy. This is called as Green's theorem in a plane. This is known as Green's theorem in a plane. Okay, sir. First, let us prove this. Then after we will see the Green's first identity and Green's second identity. Right. So here in this, we will see so here the closed curve C traversed in the positive direction. That is, you have to note that the closed curve C is taken in the counterclockwise direction. Right, sir. So that is I am drawing figure here. In XY plane, we consider a closed surface S. So here the curve is taken in the counterclockwise direction. Okay, travels in the positive. That is the positive direction. Right, sir. Now, according to the Stokes theorem, we know what is the statement of according to the Stokes theorem. According to the Stokes theorem, closed integral over C A bar dot dl bar is equals to surface integral curl A bar dot ds bar. In the previous class, we discussed this one. Okay, so this is the equation one. The mathematical expression for the Stokes theorem, we know that the closed integral over C, the line integral of A bar dot dl bar is equal surface integral of curl A bar dot ds bar. Right? Here we consider the plane closed surfaces in the xy planes. Okay. So then the curl A bar, the direction of this area vector is perpendicular to the surface outward direction. Here n cap is perpendicular to this closed surface outward direction. Okay. Now, the perpendicular to the xy plane unit vector is what? That is k cap. We know the unit vector along x-axis I cap, along y-axis j cap, and along the z-axis the unit vector is k cap. Here, the unit vector, the outward normal unit vector perpendicular to this closed surface is k cap. Hence, the area vector ds bar, small area vector ds bar, can be written as ds bar equal to k cap into ds. Okay, already I told you that very small area is a vector. Okay, here ds bar is a vector, ds bar equal to k cap into ds. ds represents its magnitude, k cap direction. Now you consider A bar dot dl bar. Consider A bar dot dl bar. So A bar, the vector field axi cap plus ayj cap plus azk cap, right? Dot dl bar is here. Since we considered the area in xy plane, only we will have the x component and y component. That is dxi cap plus dyj cap. Dxi cap plus dyj cap. Taking the dot product ax dx, we get ax dx plus ay dy. Ay dy. Here we have no k component, z component. So therefore that is 0. A bar dot dl bar equal to, we got ax dx plus ay dy. That equal to, you write it as m dx plus n gy. So comparing these two, where m is equal to ax and n is equals to ay. So comparing this, here we have m is equal to ax, n is equal to ay. And where, what is the ds? ds is the area that equal to dx dy. dx dy. Okay. Now you take the curl a bar. Curl a bar dot ds bar, that equals to curl a bar, we know del bar cross a bar dot ds bar is k cap ds. K cap ds. That equals to del bar cross a bar mod I j k dou by dou x dou by dou y dou by dou z ax ay az. In that you take the k component. Why? Because here right side we have the k cap ds. Okay, x component in the second vector, in this second vector, there is there is no x component and y component. Only we have the z component. So therefore, by taking the dot product, x component becomes 0. The dot product of y component becomes 0. Only we will have the z component dot product. So del bar cross a bar z component, that is dou ay by dou x minus dou ax by dou y into ds. So z component of del bar cross a bar is k cap into dou ay by dou x minus dou ax by dou y. So by doing the dot product, so this into ds, we are getting dou ay by dou x minus dou ax by dou y ds. Okay. So substituting these values in the statement, then closed integral over C. A bar dot dl bar equal to what we got? That is m dx plus n dy. You write that. So just we substituted that equal. So curl A bar dot ds bar equal to, we got this one. Substitute this one. Surface integral dou ay by dou x minus dou ax by dou y, but ds is equal to dx dy. This is the Greens theorem in a planes. Okay, closed integral over C a bar dot dl bar equal to surface integral curl a bar dot ds bar. To prove that, we consider a closed surface in the xy plane with a closed curve capital C that is taken in the counterclockwise direction. Then surface closed integral a bar dot dl bar equal to, we have to prove this. So here the ds bar equal to k cap into ds, and we considered a bar dot dl bar equal to a bar vector axi cap plus ayj cap plus azk cap dot dl bar dxi plus dyj cap. So that is called ax dx plus ay dy plus az into 0. We get this. This is equal to, we consider m dx plus n dy, where m equal to ax, n equal to ay. Next, you take curl a bar dot ds bar, that is del bar cross a bar dot, but ds bar equal to k cap ds substituted. So here the dot product result dou ay by dou x minus dou ax by dou y ds. ds is equal dx into dy. Substituting this a bar dot dl bar value and this value in the mathematical above expression, the closed integral line integral over the cos C m dx plus n dy is equal to surface integral dou ay by dou x minus dou ax by dou y dx dy. Okay, so this is the proof of Green's theorem in a planes. Now let us see the first identity and second identity of Green's theorem. Okay, the first identity, Green's theorem first identity. Green's theorem first identity. Okay, so here phi comma psi are two scalar functions, and consider a closed surface. Consider a closed surface, capital S, over which the functions are continuous and differentiable. The functions are continuous and differentiable. Okay. Then the expression for the first Green's theorem is the volume integral phi del square psi plus del bar phi dot del bar psi dv is equals to the surface integral phi del bar psi dot ds bar. This is the expression of Green's first identity. What is that? The volume integral of phi del square psi plus del phi dot del psi dv equal to surface integral phi del psi dot ds bar. Okay. So what is the divergence, Gauss divergence theorem? So starting with the Gauss divergence theorem, according to Gauss divergence theorem, according to Gauss divergence theorem, Gauss divergence theorem, okay, volume integral divergence of a bar del bar dot a bar dv is equals to surface integral a bar dot ds bar. First, you take this steps. According to the Gauss divergence theorem, the volume integral divergence of a bar dv called surface integral a bar dot ds bar. Now take the substitution, put a bar is equals to phi del bar psi, phi del bar psi. Okay, phi del bar psi. Here phi is the scalar function, psi is the scalar function. Phi and psi both are the scalar function in the over the closed surface S. They are continuous functions and they are the differentiable functions, right? A bar equal to phi into del bar psi. Del bar psi is the vector, phi is the scalar. Scalar into vector represents the vector, hence a bar equal to phi del bar psi. That is we considered phi del bar psi. Now, but a bar is equal to a bar equals to three-dimensional vector. What is that? Ax I cap plus ay j cap plus az k cap, that equals to phi. This is del bar psi is nothing but what? Grad psi. Grad psi is equal to I cap dou psi by dou x plus j cap dou psi by dou y plus k cap dou psi by dou x. Okay. Now comparing or equating the coefficients both sides, equating the coefficients both sides. Here I coefficient ax is equal to right side I coefficient phi into dou psi by dou x. Okay. Next to left side, the j coefficient ay equal on the right hand side, j coefficient phi dou psi by dou y. Left hand side, z coefficient, k coefficient az, and right hand side, k coefficient phi dou psi by dou x. Okay. So ax is equal to phi dou psi by dou x, ay equal to phi dou psi by dou y, and az equal to phi dou psi by dou x. Then okay, now then you take del bar dot a bar. Del bar dot a bar is equal to, okay. So what we have, what is the divergence of a bar? Dou ax by dou x plus dou ay by dou y plus dou az by dou z. That equals to dou by dou x of, just we have written now, what is ax? Ax is phi dou psi by dou x plus dou by dou y of ay, we have phi dou psi by dou y, dou psi by dou y, okay, plus dou by dou z of az, we have phi dou psi by dou z. Right, sir? Phi dou psi by dou z. So here you take the differentiation with UV method. So phi taking constant, dou by dou x of dou psi by dou x will get dou square psi by dou x square. Okay, plus dou psi by dou x taking constant, then dou phi by dou x into dou psi by dou x plus here also UV method, phi taking constant, dou by dou y of that, dou square psi by dou y square plus dou phi by dou y, dou psi by dou y plus phi into dou square psi by dou z square plus dou phi by dou z into dou psi by dou z. Okay, first second order terms you write first phi taking common, right? Dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus remaining terms what we have dou phi by dou x dou psi by dou x plus dou phi by dou y dou psi by dou y plus dou phi by dou z dou psi by dou z. So write as this dou phi by dou x dou psi by dou x plus dou phi by dou y dou psi by dou y plus dou phi by dou z dou psi by dou z. Okay, right. Also, so this is del bar dot a bar equal, but this is del square psi. Phi into this we can write as the term in the bracket, square bracket, you can write it as del square psi. So this is dou I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z dot, that is I'm writing I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z dot again I cap dou psi by dou x plus j cap dou psi by dou y plus k cap dou psi by dou z. Okay, when we do the dot product, a scalar product of these two, we will get the above expression. Okay, sir. So this is equals to phi del square psi plus this is what grad phi. Grad phi is del bar phi. Del bar phi dot. This is what grad s. That is nothing but del bar s. Del phi dot del s. So del bar dot a bar equal to finally we got phi del square psi plus del phi dot del psi. So substituting in the equation 1. Okay, substituting in the equation 1, then we get the volume integral, right? The volume integral over V phi del square psi plus del bar phi dot del bar s dv is equals to. So right side. So what is that? Surface integral a bar dot ds bar. A bar equal to, we have taken the substitution phi del bar psi. Okay, we have taken the substitution a bar equal to phi del bar psi. Surface integral a bar dot ds bar we have to write here. A bar equal, you write phi del bar psi dot ds bar. So therefore the Greens-Force theorem is proved. Okay. Now let us see the Green's second theorem. So whatever we got in the Green's-Force theorem, then simply you interchange phi and psi in that expression. Simply you interchange phi and psi. Okay. So what is the Green's-Force theorem? Green's-Force theorem expression what? That is what? So Green's-Force theorem, volume integral phi del square psi plus del bar phi dot del bar psi dv is equal to surface integral pi del bar psi dot ds bar. This is we got now. Okay, sir. This is the Green's force theorem. In this, simply you change, replace psi by phi and phi by psi. Then you will get phi equal to psi. You write in the above expression. The volume integral psi del square phi plus del bar psi dot del bar phi dv is equal to surface integral psi del bar phi dot ds bar. This is Green's second identity. Okay. So here phi del square psi plus del phi dot del psi dv equal surface integral phi del psi dot ds. So what we are doing, phi equal to psi substituted, psi equal to phi substituted. Then volume integral psi del square phi plus del bar psi dot del phi dv equal to surface integral psi del phi dot ds. Okay. Then, so this is the Green first identity, this is the Green second identity. So these are the very important theorems. The first Gauss divergence theorem, the second one Stokes theorem, and the Green's theorem. Green's theorem in a plane. So from that, we derive the Green's first identity and Green's second identity. Right, sir? So in these theorems, out of these three theorems, you will get one question compulsory. So very important. You practice and submit the imposition today before 9 p.m. Sir. Right.